Okay, so I want to put in clear relief once more and with feeling. Okay, so where we started with collisions between balls in the bubble. And I now want to extend that to say that, well, maybe the balls are exerting forces on one another, but the conservation of momentum experiments that we did have persuaded us of something we call Newton's third law. That is, that the force on ball 1 caused by ball 2 is equal and opposite to the force on ball 2 caused by ball 1, so that if I were to add the vectors together, I get 0. And we defined the force to be that is exerted on an object to cause its time rate of change of momentum. So if force on 1 by 2 is caused by number 2, it's on number 1, so the time rate of change of momentum of 1 should be the net force on 1, in this case caused by 2. And similarly for 2, the net force on 2 causes its change in momentum. And so therefore, if I add those together, I get 0. And so this is just a statement that the momentum is conserved. The total momentum, if I add together the momentum of the constituent particles of my system, which in this case only has 2, and there's nothing else, the quantity P1 vector plus P2 vector is conserved. But now I want to add in external forces. So the notation is going to get a little busier. So I'm going to consider the time rate of change of the momentum of particle I. So dp I dt, well, that is caused by all the forces on particle I. So that includes the force from every other particle in my system, J, plus whatever external forces are applied to I that come from outside the system. Okay, so I'm considering now a system of a bunch of particles that I can index with I or J. And what causes the change in the momentum of any one of those particles is the sum of all the forces, both internal and external, that are applied to it. Now, for your pleasure, I'm going to sum over all the different particles. Yeah, cough, cough. Okay, so this is now going to be a double sum. The first sum was to say, all right, if I'm particle 1, you got to add up the forces on me from particle 2, particle 3, particle 4, and so forth, plus whatever outside forces there are. And now I'm saying, yeah, do that, but then also add up for all the particles in the system, because actually that's going to simplify things. So I've written in red this sum over all the internal pairs of particles. And can someone make the argument for me why the red sum disappears? It must sum to 0. Yeah?
Because that represents the interactions between all of the particles in the system, and so for every force of like I on J, it's canceled out by the force of J on I.
Exactly. So in this sum, for any pair of numbers I and J, so let's say 1 and 2, there's going to be once the term F12, and there will be once the term F21. So I can just reshuffle all the terms in the sum, and 2 by 2, they wipe each other out. And so the whole sum disappears. So that means that the change in this momentum of the sum, so I sum the momentum of all the particles, that's the total momentum of the system. I can then take the time derivative. So I'm just exchanging the order of differentiation and summation. Is that legal? So I can take the derivative of the sum term by term, so that certainly is legal. And so this is the left-hand side. The right-hand side is now the sum over all the external forces on all the particles in my system. And so this says that the time rate of change of the whole momentum is equal to the sum of all the external forces on the system. And this, as we will see, allows us to apply a system I'm going to call divide and conquer. And we'll see what that means as we apply it to a bunch of different examples. But it says, if you want, pick any system you like. Having identified what your system is, now some things are inside and some things are outside. This tells you the rules for how to add up the consequences for the inside and the outside influences.